Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, Smoke Detection, Challenges, Regulations, and Solutions. Discussing today's topic are Grania Murphy, Marketing Manager, Analog Devices. Grania Murphy is a Marketing Manager with Analog Devices Industrial and IoT Solutions Group. With over 25 years of engineering experience, she manages customer needs, engagement, and marketing and communication strategy for ADI's key product portfolios and future direction within building automation. And joining her today is Kevin Buckley, Applications Engineer, Optical Sensors Group, Analog Devices. Kevin Buckley is an Applications Engineer with the Optical Sensors Group. He has been with Analog Devices since 1990 and has served in a number of roles. It's with great pleasure I now turn this special session over to Grania to begin. Grania, take it away.
Thanks a lot, Chris. It gives me great pleasure to welcome you all today to our Analog Devices webinar on smoke detection. As Chris has introduced us, my name is Grania Murphy. I'm the Marketing Manager for ADI's Intelligent Building Solutions Group, and I'm joined by my colleague Kevin Buckley, who's an Application Engineer with our Optical Sensing team. We're going to split today's webinar into three parts. The first piece I'm going to talk through, and it will introduce some of the economic and market situations and trends. These provide both challenges, but also great opportunities within the smoke detection market. I'll also cover the regulations and some of the test requirements for worldwide certification in smoke detection. And then Kevin will bring you through the detail of optical technology in relation to smoke detection and share some of our data from the latest test results. And then finally, I'll conclude with some ADI solutions and further places you can access to get more information after this webcast. It's important to recognize the macro trends that have an effect on early fire detection. The first one is urbanization. As the world's population increases, the biggest trend and the highest growth rate is the movement into cities. The International Energy Agency notes that growth in global buildings floor area is about 3% per year, and this is therefore leading to higher density housing and commercial buildings. Today's buildings are designed to hold thousands or even tens of thousands of people within. So the management, and in particular the safety of people within them, is paramount. Global buildings are estimated to use 40% of total energy today. So any technologies that can lower energy consumption are critical. There's also the environmental concerns. Buildings contain synthetic materials. Therefore, early fire detection is critical in the balance of fighting any scale of environmental impact from large-scale disasters. And finally, and critically, regulations are driving most change in both environment and safety. In smoke detection, each revision will always become more stringent. And even at local level, they will always focus on better detection and faster alerts for human safety. When we talk about the dynamics of an intelligent building, there are some trends to understand. JLL, who are a world leader in real estate services, talk about the 3-30-300 rule. This illustrates the average order of magnitude between a company's cost for utilities, rent, and payroll, and this is all per square foot per year. So for every $3 of utilities, you pay $30 for rent and $300 for payroll or people cost. So if you relate this back to smoke detection, any false evacuation of a building has a big impact on running cost. The industrial or the building IoT trend shows that all the sensors within a building are now required to be connected into building management systems, and therefore smoke detection design needs to factor this in. And finally, with digitization comes choices on how to partition. Intelligence, or smoke detection algorithms at the edge versus the cloud, have implications on bandwidth processing and cybersecurity. And with regulation driving faster alert times, delays due to latencies are not an option. The regulations are basically supporting the reduction or elimination of fault detection and the faster of evacuation of buildings, but ultimately the true value is actually saving human lives. Now let's move to the regulations, but firstly, let me explain that there are two predominant smoke detection technologies. Ionization systems, which have a small amount of radioactive material between two electrically charged plates. This ionizes the air and causes current to flow. When smoke enters the chamber, it reduces this current flow and activates the alarm. However, some European countries and US states have actually banned the use of ionization detection because they have not always detected early state fires. The second technology is photoelectric or optical smoke detectors. Inside the alarm, there's a chamber that uses light to detect smoke. When smoke is present, it deflects the LED light into a photodetector, and as soon as the light hits this sensor, the alarm is activated. Smoke detector systems need to be fully tested as an end product. But there's also testing that can happen at the subsystem level. This does not substitute for full certification, but it can give peace of mind before costly end system testing. There are basically 5 main global standards to compare. They all have different requirements to pass the respective certification. In the US and in Canada, there's UL 268, the 7th edition, and UL 217, the 8th edition, both of which are pending. The biggest change in these standards includes updates to the polyurethane flaming and smoldering and cooking nuisance, or what we call the hamburger test. For Europe, there's EN 14604 and BSCN 54, which is the British standard. And the piece that's most relevant here is Part 29. For international standards, there's ISO 7240, and the relevant part here is Part 7. And for China, they follow the 2003 edition of ISO 7240. It is a requirement to meet the relevant standard for the country in which the device is targeted to be installed. However, as we'll detail next, it's fair to assume that if you pass UL 217 edition 8, you have a good chance to meet the other standards. The flaming poly versus hamburger or cooking test is challenging due to the similarities in smoke profiles, and this may be a reason why UL, as detailed here in their official notification, have delayed the implementation by a year out to June 2021. And each regulation has a different set of rules for testing. For example, UL 268 and UL 217 require 28 test specimens, all of which are used for each test. For the other 3 standards, the specimens are numbered as detailed, and unique specimens are then required to pass specific tests. So as you can see that for global compliance, each test in each standard must be performed and standards cannot be overlapped. But it also extends to the conditions of test. However, EN 54, EN 14604, and ISO 7240 have identical requirements for the smoke tunnel and fire room, so the testing can at least be performed in the same location. And there are also a multitude of other test conditions. I'm just showing one example of these here. But the biggest takeaway is that one size does not fit all, and that testing is a timely and costly process. So to close our first part, the biggest challenge of smoke detection is understanding and passing smoke regulations that are becoming more and more stringent. As smoke detection moves from standalone to connected network devices, size is an important factor. Customers are looking to change the design aesthetics of traditional smoke detectors, as well as place smoke detectors in harder to reach locations, such as in transportation. Aligned with size is power, where better detection is now required for less power. In batteries, it means either smaller batteries or longer life with the same battery. On mains powered, it means being able to add more detectors on loops like 4020. And then finally, there's the challenge of getting to market quickly in light of time-bound regulations and understanding the total cost of ownership, not just from a bill of materials, but from a manufacturing and platformization benefit. So I'm now going to pass you over to Kevin to bring you through the next section.
Thank you, Grania. All right, so I just want to go through several slides here to describe the technology behind our optical smoke detection measurement. The first slide here just shows how we perform an optical scattering measurement here to measure the smoke. So basically the units that we talk about when we're discussing the level of smoke being detected is PTR, which is a power transfer ratio. Basically what this is the power received at the photodiode per power supplied to the LED. And the reason we look at the signal in terms of PTR is because it kind of takes out the configuration of the device from the measurement. So the PTR of the smoke is a consistent number regardless of, for example, how much LED drive you're providing or the number of pulses you're taking per measurement, what the TIA gain setting of the device is. So it takes out all of these configuration variables and puts it into a single number that always reflects what that level of smoke is. Okay, so it's a dimensionless quantity that effectively allows easy scaling. So with our device, the optical detection, the scattering of the particles is performed directly above the module. Okay, so the LED shines light directly into the space above the module. Smoke particles enter the optical path, and light reflects off of these particles back onto the photodiode. Okay, so when there's a smoke chamber involved, which basically controls the environment around the smoke detection module, you're going to end up with a little bit of background response based on that chamber, because the module is a very sensitive measurement. So anything in the optical path up to, it could be a couple centimeters to a couple inches away is going to give you some type of background response. So this introduces a couple of challenges, namely that you design a chamber that really reduces this background response to a level that is going to be relatively insignificant when you're trying to measure this small smoke signal that's there at the same time as this background response. So some of the things that have to be done here at the system level now is to actually null out that background response, which we call here a background subtraction. So you're going to have, your chamber is going to give you some initial background response, at time zero, let's say, when the smoke detector is first turned on. And then over time, you may get some slowly varying signal changes in that background response due to long-term dust accumulation. It could be some type of grime or soot from previous smoke events that build up just over time with a smoke detector being on your ceiling for 5 to 10 years. So in the background, there would need to be some algorithm that helps to eliminate this background response. And it's really a simple kind of long-term high-pass filter that can filter this signal out. Now, the golden standard of smoke detection measurements when you're talking about optical smoke is an obscuration sensor measurement. So when you take your smoke detector to, for example, the Underwriter Laboratory who created the UL 217 spec, what they have is a light source and a detector that's about 4 or 5 feet away, and they have some signal when there's no smoke present, okay, and it's basically 100% signal. And as smoke enters this beam, it starts to obscure the beam so that the signal being detected starts to reduce. Okay, the way that an optical smoke detection module like the ADPD-188BI makes the measurement is effectively the inverse of that. Okay, so when we're shining our LED and there's no smoke present, we get no signal back, whereas an obscuration sensor gets 100% signal back. As smoke enters our optical path, now we start to get a signal based on the scattering of the smoke particles. And with the obscuration sensor, that signal actually starts to reduce because the beam is being obscured. So the trick here is to prove correlation between this golden standard obscuration measurement done at UL to the type of scattering measurement that we do on our module. And basically what we show here is just a form of correlation where the PTR of our measurement in nanowatts of received current for every milliwatt of provided LED power correlates to some obscuration level, beta, times some lambda, which is going to be some scalar based on the smoke type, the module geometry, and whatnot. This slide goes into a scattering angle heat map, which shows when the smoke enters the optical path, where most of that smoke is being detected. So as you can see here, we have a module it's a really small form factor module. It's like 3.8 millimeters by 5 millimeters. Okay, and what you can see here is that most of the smoke that's being detected, or what's providing you the strongest signal, is the smoke that's really in the first millimeter above that module. Okay, now what this does is it provides you a solution where you really don't need a lot of smoke in the path to receive a relatively strong signal. This means that we don't have to provide a whole lot of LED power to be able to detect that signal. So when we go to this small form factor module with a design that's going to detect smoke that's literally tens to hundreds of microns away from the optics, it provides you a very small form factor, low power solution. This slide goes into the full smoke detection solution. So, for most smoke detectors on the market today, there's going to be some type of smoke chamber that encloses the optics to control the environment for airflow, for keeping insects out, for reducing ambient light into your optics. So because of the unique way that we measure the smoke, whereas we're measuring the smoke directly above the module rather than in some more forward scattering type method that shoots a beam at an angle across the top of a PCB and receives the signal into a photodiode, up to 5 to 10 centimeters away. We've had to design our own chamber to deal with the new challenges presented with the method that we use. So a lot of engineering has gone into this chamber, and we've got it to the point where the PTR of the chamber is on the order of 3 to 4x the level of the PTR of the actual smoke we're trying to measure, which leaves you plenty of dynamic range with the analog front end that we use to be able to measure that, to still be able to measure these small smoke signals that enter the optical path. Alternatively, if you wanted to go with a chamberless design, the AD-PD188BI is actually probably the most ideal solution for a chamberless design because of the analog front end that's integrated inside this module. The analog front end that we uses very short LED pulses on the order of 2 microseconds, 2 or 3 microsecond pulses. And what this provides you is exceptional ambient light rejection, because you're able to chop that DC frequency with this DC ambient light frequency with these very, very short LED pulses. So this provides an ideal solution for a chamberless detector where the environment's not going to be controlled and you do have to deal with ambient light. So this slide here shows some data that we've received testing at the UL labs. One of the things about the AD-PD188BI module is we use 2 wavelengths. We use a blue LED and an infrared LED, along with integrating the photodiode and the analog front end in the package. But by using these 2 different LED wavelengths, we're able to start to get some particle size differentiation based on the response to those 2 wavelengths. So the ratio of the blue to the infrared response will change as the particle size starts to drop below probably between 1 and 2 microns. So once you start getting into the realm of smoke particle sizes, which are all like less than a micron in diameter, you start to really get a different ratio in the blue to infrared responses versus, for example, water vapor, which is a particle that's generally much larger than 1 micron in diameter. So the plot on the left here shows some of the ratios to the smokes that we test at for UL. EN has similar smokes. All the standards basically have many of the same types of smokes that they're trying to detect. But what this shows you here is that each of the different smokes are coming in at a different ratio. On the far right, what we have here is a ratio for steam, which you can see comes in much lower than most of the smokes. It's a little bit lower than the smoldering polyurethane smoke, which tends to be a bigger particle. But even with that one, you're still at a level where the ratio provides you enough margin to differentiate steam from the smoke. One of the issues here with just trying to determine ratio, for example, Grania mentioned the cooking nuisance test earlier, also known as the hamburger test. So basically what that hamburger test is a way for the standard to force smoke detectors to be able to differentiate between a nuisance source and an actual smoke source. So the idea is that the threshold has to be set. It has to be set high enough that it doesn't alarm on a certain level of hamburger smoke or cooking smoke, but low enough that it will still alarm for any of these valid polyurethane smokes or wood smokes or paper smokes. The threshold has to be low enough so that it still will alarm for any of the legitimate types of sources that you're trying to alarm on. So what this ratio plot shows you is that, hamburger smoke, it's a legitimate type of smoke with a smaller particle size, so you're really not going to be able to identify that with the ratio test because it falls right in the range of other smokes. Okay, on the right-hand side, we show the actual PTR levels of all the different types of smokes. So in this case, what you see is that on the far right of this plot, the hamburger test is the smallest amount of PTR. All right, so at the threshold level that you need to set in order to avoid setting an alarm in the presence of hamburger smoke at the obscuration level determined by UL, that PTR is lower than the PTR of any of the other legitimate smokes that we do need to set an alarm on. Okay, so you can see that the one that's the closest is the flaming polyurethane. So as long as we have enough margin between our PTR measurement on flaming poly versus hamburger, then your smoke detector will be able to pass that cooking nuisance test for UL. And this plot just further illustrates that point, really just zeroing in on those two specific types of smoke that I mentioned, the hamburger versus the flaming poly, which is the closest PTR to the hamburger. So as you can see here, on the left you have the blue response, on the right you have the infrared response, and this is using our ADPD-188BI module along with our chamber, and it shows you that there's a little better than 10% margin there, where you can set your threshold to not trigger on the hamburger smoke, but still trigger for any of the other valid smokes. This slide here just shows the sensor response summary for all of the UL tests. So at the bottom you have the dashed line where we would set our threshold based on that flaming polyurethane fire that's high enough that you don't trigger on the hamburger. And all of the other different types of smokes fall well above this threshold. So you see your smoldering wood, your smoldering polyurethane, your flaming wood, and your paper fire. And they all fall well above the threshold that you would set based on the polyurethane. This slide here shows a summary of the sensor response from the EN tests. So when we go to the UL labs, they also have the ability to do the different any smoke sources that are tested by EN that are different from UL. They actually have the capability to set that up there as well. So we've also run it through all the different types of EN fires. And basically what this shows you here is that the threshold that we've set based on our UL testing, based on that flaming polyurethane level, is still below all of the EN fire types. Okay, so basically with a single smoke detector and setting your threshold based on the flaming polyurethane test from the UL standard, you're able to pass all of the UL 217 specs as well as all of the EN specs. Okay, moving on from the specific smoke tests, I just wanted to get into a couple other features of the ADPD-188BI module. This here is a representative power dissipation plot, which shows, at a 1 hertz sample rate, which is about what a smoke detector will probably operate at, right? I mean, it'll check for smoke 1 time per second, maybe a little less, maybe a little more, but right around there. The signal to noise ratio required is generally on the order of about 20. And when I say 20, that's not 20 dB. It's just a signal-to-noise ratio of 20. So 20x the signal versus the noise is a typical level that any algorithm will be able to deal with. And what you can see here is that, basically, if you're just trying to detect smoke with infrared, which would be a way to just detect that there's something there without even flashing the blue LED until you've actually detected something with IR, you can operate at less than 10 microamps, or less than 10 microwatts of average power. And then once the infrared signal actually detects something present, some type of smoke present, you can start to flash the blue as well, at which point you're going to go up to maybe about 15 microwatts. Okay, so it's a very low power solution. This here is a plot that shows how you would account for dust or grime buildup on the chamber. Now, one of the things to keep in mind is that in a standard optical smoke detector, the way that the optics have traditionally been designed, there's no background response. All right, so unless smoke is present, which normally it's not, there's really no way to know that your optics are working. Okay, one of the things that makes our design a little bit challenging is having to deal with the background response of the chamber. But once you've figured out how to deal with that background response, it actually provides you a lot of self-diagnostics of what's going on inside your smoke detector that otherwise wouldn't be available. For example, just to determine that your optics are working, it's a simple measurement right off the chamber and you can see that you're getting a signal. The other thing that you can do is measure how much dust is accumulating or grime, right? So, if over time you're getting a lot of dust accumulation or grime accumulation, it may get to the point where you want to trigger an alarm for the user to either replace the smoke detector or open it up and clean it, right? If you think that the degradation to the actual smoke signal detection is going to be affected. So basically what this shows here is the way you would kind of account for dust or grime over time. So at time 0, you take a measurement, you get some PTR off the chamber, and then as time goes on, you can continually just take measurements off the chamber, and as that response changes, it's due to some type of buildup on that chamber. And you can just simply account for that in your algorithm and set yourself with the new operating point when you're nulling out that background response. One of the other nice features of the 80PD188BI is that we have this on-chip non-volatile memory, right? So we have these eFuses on chip where we can burn in on-chip calibration. Okay, and what this provides you is the ability to get better than 10% device-to-device variation for every part that you ever put on one of your PC boards in your smoke detector. Okay, so if you can guarantee that each device is going to be within 10% variation, this may allow you to eliminate an actual calibration of each smoke detector at end-of-line testing in a smoke chamber. Okay, because if you know that every part is going to be within 10% of the previous part, you can do a characterization while you're developing your smoke detector and be able to eliminate this last step calibration with an actual smoke source and still guarantee that everything is going to be within 10%. And the UL limits are 25% margin. Okay, so the 10% is well within that margin. Okay, at this point I'm going to hand it back to Grania to finish off the presentation.
Okay, thanks, Kevin. Well, Kevin has brought us through some of the actual test results, and I just want to do a quick summary here. I mean, firstly, the test data shows that we do meet the obscuration targets to meet the standards, and that the solution achieves a lower power due to that high efficiency and shorter distance when measuring the light. And this leads to large power savings by design, so you can see that he explained how we're in the microamp and microwatt range. And because of the in-test calibration that we can perform, it can significantly either eliminate or reduce any system-level calibration through the final product manufacturing process. So that has a cost implication. And then also, from a cost perspective, when you actually compare against an integrated solution, you reduce the cost of maintaining that supply chain, and you reduce the risk of a line down as you've less components, and the reduced form factor size opens up more design options, or it can open up a platformization approach across your end product portfolio. But most importantly, I think we've demonstrated that our optical sensor and smoke chamber can pass UL 217268, and we're actually pending formal certification listing. So to very quickly summarize the ADI solutions, the ADPD188BI is an integrated optical module that contains an AFE, photodiode, and LEDs in one package. The associated smoke chamber, which has been designed and is licensed by ADI, has low attenuation, resistance, and light scattering, so that the PTR measurements is replicated very accurately inside the chamber. Of course, many customers have their own existing smoke chamber solution, but this is available to those of you who don't, or maybe those of you who are actively looking for reduced form factor smoke detector solutions. This is the smallest smoke chamber. It's just 20 millimeters diameter, and you can order samples from ADI, and then in volume our production quantities will be managed by our partner Accumode. So we talked through listing solutions, but I just want to very quickly bring you through a smoke tool that's in process right now, and this is going to focus on the software algorithm for UL certification. But just looking at the hardware for the moment, it's designed to be an Arduino form factor smoke detector reference design for prototyping and development. The ADPD188BI forms the basis for the analog particulate measurement, but the reference design will also enable customers to handle nuisances like humidity using heater resistors to dry the air inside the smoke chamber, and it comes complete with things like LED indicators and a micro SD slot for storing data. But the key part of the solution will be a software algorithm that will be developed using test data. And currently, we're gathering many hundreds of smoke and fire test sample data sets from the UL 217 test configurations. This algorithm will focus on UL 217 alarming certification, so those key areas of smoke versus non-smoke, which translate to the real alarm versus the nuisance alarm. And it's going to be designed using various layers and protocols as shown here, so that it can be simply stitched into any design with any microprocessor system. So that's given you a look about what's in process, but back to what we currently have available from ADI. So just to share some of the tools, we have an ADPD188BI evaluation board available. It requires a motherboard to run, so the Eval ADPD-UCZ, which is available from ADI. So have smoke chamber samples in packs of 2s and 10s. So just to reiterate, ADI owns that smoke chamber IP, and when you break the seal to the samples, you sign up to the fact that it's licensed by ADI. Also have several application notes. As Kevin mentioned earlier, the ADI in-test calibration can save you time and cost during the final system test process, So this calibration note might be particularly useful to help you unlock this value. Article you might want to download is my article on certification, which goes into the regulations in a bit more detail. I'm highlighting the product pages and where you can access software drivers, but also don't forget ADI's Engineer Zone, where you can post a question and our experts will get back to you as soon as possible.